Hello everyone, welcome to the pre-lab lecture for Fischer Esterification for Orgo 2 Lab. So starting out in this experiment, for a Fischer esterification, you're looking at a reaction of an alcohol and a carboxylic acid. And this is also acid catalyzed, so we do see sulfuric acid there. Um, and you're going to have a few possibilities of what can be made because there are actually, and one of these is cut out, but there are three alcohol possibilities and there are three carboxylic acid possibilities. And so you'll see a table of what I'm talking about, but um, based off those combinations of possibilities, we're going to see specific esters that can be made. All right. Now, in this reaction, uh, big thing here, esters have this carbonyl group, and then that carbon is also singly bound to an oxygen. All right, not in the form of an OH or an alcohol-looking group, but in the form of OR. So there's got to be some other like alkyl chain or ring or some carbon-containing functional group or branch there, okay? And so as we said, we see a carboxylic acid reacting with an alcohol. It is acid catalyzed, and we'll talk about why that's important in a second. Okay, another thing to kind of notice here is in this reaction, you make an ester, but you also have water as a product. And so that can come in handy in terms of looking at this reaction when we look at the arrows here. All right, this reaction is in equilibrium, so it doesn't just want to push forward and create nothing but the ester and water. It's got a balance to it based off its equilibrium constant. All right, and so big thing here, thinking about this in terms of this is an equilibrium reaction. There are a couple of ways that you can manipulate the conditions for this reaction so that you can push it forward and make more ester. One of the things that we can do is, well, first off, we will be looking at this in terms of Le Chatelier's principle. All right, so that nice little principle back from Gen Chem 1, Gen Chem 2. All right, so in Le Chatelier's principle, we know that there's a few things that we can look at. Predominantly, if we look at concentrations, right? So we know that the equilibrium constant is in essence the concentration of our product over the concentration of our reactant, right? And so um, in order to push this more and more, we know Le Chatelier says, okay, so if we start to see very little product, right, equilibrium is going to force this reaction forward, right, to make more of our product. However, if we see that we're making too much product, it can actually say, oh, no, we're going to go in the reverse and we're going to go back to the carboxylic and the alcohol. Okay, so what are some ways that we can use Le Chatelier's principle to help us push this forward and make lots of ester? One of the ways we can do this is we can use alcohol as a solvent, right? When you do that, when you're using it as a solvent, you're using large an excessive, ridiculously so, excessive amount of alcohol. And so what it is you're keeping this relatively high concentration of alcohol and it's saying, oh no, equilibrium is favoring too much on the reactant side. We have to push to the product. And you could actually wind up getting to the point to where you can consume almost all of your carboxylic acid, not all of it, but close to all of it, and make a lot of your ester. Okay. Another thing you can do is sequester water. So what does this mean? That means that as you're producing water here as a product, right, as you produce it, if you use something like molecular sieves that absorbs water, right, in essence, that's decreasing the concentration of water, or it's removing product, right? So as you're removing product from the reaction, it's saying, oh no, we need to make more product. So you're going to push it based off Le Chatelier, you're going to push it to make, as a consequence, water, but also more ester. Okay. Another thing that they talk about is using solvents that can form low boiling point azeotropes with the water. So there you'd have to look up a list of these. This isn't something that we heavily teach in terms of what forms azeotropes. But if it forms an azeotrope with water, in essence, it no longer looks like water, right? So it falls outside of your equilibrium. And so it's kind of like the water is disappearing. Okay, so it's kind of similar to using molecular sieves to absorb the water and it disappears. Okay. Um, Another thing you can do is distillation. In particular for this reaction, Fischer esterification, if you look, you have an alcohol and you have a carboxylic acid. Both of these are going to have relatively high boiling points because they can do hydrogen bonding, right? We know that that intermolecular force will give very strong physical properties to these generic molecules. While comparing it to the ester, it can no longer hydrogen bond. It is polar, but its polar interactions aren't going to be as strong as hydrogen bonding, so it's going to have a lower physical property like a boiling point. And so if we did something like distillation, this is going to have your ester right here is going to have a lower boiling point than either one of your reactants. So as you're boiling it off, right, it's like it disappears from solution. And so Le Chatelier is saying, oh no, make more of our ester because we don't have a high enough concentration of product. And so you could distill it off. And one way, we're not actually going to distill. The way you're going to set up the glassware for this is not going to be a distillation. It's going to actually be a reflux condition, but that kind of follows a very similar thought process as distillation in that when you're refluxing, you're going to boil the solution. And what's going to boil first? The compound that has the lowest boiling point. And so the compound that would have the lowest boiling point here is going to be your ester. So it's going to be up in the vapor phase. All right, and then it will eventually get condensed back down, but that, in essence, what that's doing is that's kind of tricking the solution into thinking that there isn't any product or any ester product there, and so it's going to keep making it. Okay. Now, as I said before, we do have 1, 2, 3 different alcohols and 1, 2, 3 different. Oh, sorry, 1, 2, 3 different alcohols and 2 different carboxylic acids. And so, with this, these are the 3 possible esters that you could make when you look at these specific combinations, right? So you're looking across here when it's isoamyl alcohol with acetic acid, you're going to make this isoamyl acetate and it's going to smell like bananas, right? And so you can actually use the smell. You don't want to directly sniff the compound, but you want to waft it. I don't know, but you kind of like hold up the container and you just use your hand to kind of wave the smell towards your face, okay? That's always a good practice. Never directly smell anything. Sometimes you could faint. You could get knocked out by certain aromas or fumes that come off of reactions. So never directly smell anything, just like you would never directly taste anything. Okay. Anyway, so with that, this smell, not flavor. We're not tasting anything. Okay. Don't pay attention to flavor, but the smell. That's what you're going to pay attention to. Okay. And so here we also see the pre-lab questions. They do ask that you draw the structure for the ester product. I mean, in order to draw the ester product, it's also a good idea to go ahead and just kind of draw out simplistically the reactions like we see here, right? Acetic acid, 1-propanol makes the propyl acetate, right? So you want to do something generically like this with the other 2, because technically that's reaction number 2 right there. All right, so go ahead and do it for reaction 1 and reaction 3 also, okay? And then also looking up the boiling points for the alcohols and the esters in each one of these, right? Because you do want to kind of pay attention. You do want to be careful because these alcohols and esters, they're not similar molecular weights. So the molecular weight can also affect the boiling point. So you kind of want to look at those and check and see, because if some of them are really close in terms of how close they are to boiling, then you could actually be boiling both of them off at the same time. And so what's going to happen if you're boiling off both an alcohol and an ester, right? If you're boiling off both a reactant and a product, right, you're really not you're not using Le Chatelier's principle correctly, and so you're not really going to force this reaction to go in one direction over the other. Okay, Now, some things to kind of talk about here because you just keep seeing these reactions generically, but I do think it's important for you to understand these reactions mechanistically. So when we look at this Fischer esterification, right, I just picked something random. This is not one of the specific reactions you'll be doing today, but if we know that we have a carboxylic acid, right, reacting with an alcohol, right, and this is acid catalyzed. Okay, so this will get used up, but we'll regenerate it somewhere along the way. Okay. Now, so what we're going to see here in terms of these two reactions, anytime you see a carbonyl, right? Anytime you see C double bond O and an acid, the very first thing that you're going to see happen is that a lone pair from that carbonyl oxygen is going to take a hydrogen. This is going to act basic. I know it's very unusual to think of because this is a carboxylic acid, yet it's going to act like a base. WTF, mate, right? I get it. But anytime you see a carbonyl and an acid, I don't care if that acid is HCl, I don't care if it's HNO3, I don't care if it's H2SO4, I don't care if it's H3PO4, right? I could keep listing them, but you don't want this video to be 45 minutes long. If you see an acid and a carbonyl, period. It doesn't necessarily have to just be a carboxylic acid, right? It could be an acid chloride, could be a ketone, could be an aldehyde, right? You see a carbonyl, protonate that oxygen up there, okay? So we're going to see a lone pair attack a hydrogen, and then we're going to break this oxygen-hydrogen bond, and so now we're going to get water, and it'll be neutral. Okay, which I don't really show over here in this product step, but you do make the water. It'll come back later. Okay, now what we see happening here, now our carbonyl oxygen has become positively charged. And what has this done? This is, in essence, if you think about a carbonyl carbon, or if you think about a carbonyl period, right? That's partial positive, that's partial negative, right? We know that carbon is partial positive and oxygen is partial negative based off of electronegativity, right? This is a polar bond, and oxygen's more electronegative. All right, so what's happened now that you've turned the oxygen, you've given it a positive charge upon reacting with an acid? Well, this carbon was already a little stressed out, but now it's even more stressed out because now this electronegative oxygen is not happy to be positive. So in essence, what you've done is you've turned this carbonyl carbon from being sort of electrophilic to now super electrophilic. All right, and now that that has happened, you can see that the one of the lone pair off of our oxygen of the alcohol can attack the carbonyl carbon, kick this pi bond up, and kind of relieve the positive charge on that oxygen. So what you're going to see is something really weird. You're going to see what once was our carbonyl carbon now has two alcohol groups on it. Totally strange, right? And then you've got a third oxygen connection where it's still got a positive charge, and it still has a hydrogen here from that alcohol originally. Right, so what's going to happen? Well, nothing in here is necessarily a great leaving group. Technically, the alcohol functionality right here, that's that once was the alcohol itself. That's a pretty good leaving group, but what you're going to see happen instead is a lone pair, and this is happening in equilibrium. Okay, so what you're going to see happening instead is a lone pair from one of these alcohols is going to take that hydrogen, all right, and then break the oxygen hydrogen bond here and satisfy the positive charge there. So now what's happened? You've turned that alcohol into water, which we know from E1, E2, SN1, SN2. When we talk about those, we talk about leaving groups, right? Water is a superb leaving group, right? So it's ready to say bye-bye, right? So it'll kick off while the lone pair on one of our other oxygens, the alcohol oxygens, kicks down and regenerates that pi bond. All right, and then what we kind of see the exact opposite of what happened in our very first step here, carbonyl reacting with an alcohol. Carbonyl reacting with an acid. Right, so we have this carbonyl oxygen now that has a hydrogen. It's got a plus charge. So water can now come in and take that hydrogen. Why does that happen? See up here, we had the acid that was a catalyst. And what is this going to do? This attack right here is going to regenerate that catalyst, right? So you can see we get our, um, you can see we get our ester and we get our acid catalyst regenerated. Okay, now, um, now do keep in mind here, right? This turned into water, right? So technically we do have a plus water here, right? And then if you notice also here, we kicked off water. So technically now you have a water that was up here and a water that was up here. Okay, so uh, two waters, right? This water, let's just say that water is that water, right? So we turned that water into the acid, regenerated it. But this one never did anything, right? It floated off and it was like, doo 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 doo. Hi, my name's Paul. All right. So as the overall product, right, we do see, as our overall products, we do see ester and water product. And then we kind of ignore this because, right, it was up there, it just got regenerated. So it's kind of like nothing ever happened with it. Okay. Now, next up, the other thing I wanted to talk about, in particular, your directions for your procedure tell you a few things. All right. After you've allowed this reaction to happen, there's a couple of things that start happening. You're going to take that reaction mixture and you're going to put it in a separatory funnel, and then you're going to rinse the round bottom flask and the separatory funnel with ice water, and then you're going to use that same ice water with the separatory funnel. Okay. Now, so in essence, you're going to wash the product with ice water. Then, after you've done that in the separatory funnel, you're going to take the organic phase and you're going to react it with sodium carbonate, or you're going to throw in a sodium carbonate solution, and you're going to do that 2 times in the separatory funnel. Then it says you're going to have saturated sodium chloride, a brine solution, which is in water. This is an aqueous solution. So you have an aqueous wash step, an aqueous wash step, an aqueous wash step. So my question comes to you: what is the point of sodium carbonate? Okay, the big thing here is you can't really say that the point of the aqueous, or sorry, the point of the sodium carbonate is to wash, right? Because you've got all of this. If you think about it, you're you're trying to help remove water from the reaction, but then in the next set of separations that you do, you throw in more water. That should be a big red flag, right? Sodium carbonate here is not a drying agent, all right? It's not meant to remove water. It's doing something else. Okay, so if you remember back in the day from Gen Chem 1 and Gen Chem 2, sodium carbonate is actually a basic salt. Okay, so it being a basic salt, what do you think that means? If it's basic, what's it going to react with? Hopefully, you're thinking, or you just said out loud, it's going to react with an acid, right? So bases react with acids. So something kind of generically that we would have seen back in the day of Gen Chem 1 and Gen Chem 2, if you have your sodium carbonate, it reacts with an acid. You see that it makes sodium chloride, a neutral salt, and it makes carbonic acid. Now this H2CO3 rapidly degrades into both water and CO2. All right, so proof that a reaction has happened, you see the formation of CO2, a gas. Okay, now you don't have HCl present in your reaction mixture. What do you have that's present as an acid? You have a carboxylic acid, right? So you're pretty much going to see something very similar. You're going to see your carboxylic acid reacting with the sodium carbonate, right? And what's the big thing that happened up here? CO3 got hydrogens, right? So if CO3 gets hydrogens, that's the only the acidic hydrogen that it could get. Okay, so that means that now this acetate ion is going to kind of migrate with the sodium, so you'll get your water-soluble salt, and you'll make carbonic acid, which turns into CO2 and water. Okay, so what does this really do? What does the sodium carbonate really do? It reacts with the acid so that we can remove it, right? Here, this acid is really, this carboxylic acid has a lot of carbons in it, so it's very soluble in an organic layer, right? So by salting it, reacting it with sodium carbonate and salting it, you make it, now it's water soluble and it's not organic soluble. Okay, so you push it into the water and you can now remove it. All right, so that's something to keep in mind. All right, at this point you should be prepared to take your pre-lab quiz. Good luck.